This is gases video number 4. By the end of this video, you should be able to calculate pressure, volume, and temperature of a gas under changing conditions. To do this, you will need your gases video number 4 worksheet, a pencil, and a calculator. Also handy will be your various formulas that you will need. These formulas are in your packet, but they were formulas that we'll be using so often that you will be memorizing them, and in fact will have to have them memorized on a test or a quiz. Let's get started. Example number 1. A gas has a volume of 14.5 liters at a pressure of 725 torrs. What is the pressure if the volume is increased to 20 liters? So our variables are V1 is 14.5 liters and P1 is 725 torrs. So our initial or first conditions are 14.5 liters and 725 torrs. V2, or the second or new condition, is 20 liters. The new pressure is what we're trying to find out. Now before we go on, we want to make sure that our units are good. Volume is in liters and it goes to liters. Since these units match, we can use them. Pressure starts off in torr. It ends in some unknown unit, but this unknown unit, since it has to match, will end up being in torrs. Now let's take a look at our variable sheet. In this case, pressure and volume are changing, and we're assuming that temperature and number of moles are constant, since they didn't tell us otherwise. So the formula we're going to use is P1V1 equals P2V2. Let's write that in. So P1V1 equals P2V2. Let's rearrange this so we get P2 by itself. To get P2 by itself, I need to divide both sides by V2. So that the V2's cancel on this side. I'm left with P1V1 over V2 equals P2. I'm now going to plug in my numbers. So 725 torr is P1. V1 is 14.5 liters. And V2 is 20 liters. After I'm done multiplying 725 times by 14.5 and divided by 20 liters, liters cancel, I will end up with 526 torr. This is rounded, and this is my final answer. You also want to double check to make sure it makes sense. Volume and pressure are inversely proportional, so when one goes up, the other one goes down, and my pressure did go down, so the number does make sense. Example number 2. A gas has a pressure of 1.15 atm when the temperature is 24.8 degrees Celsius. What is the pressure of the gas if the temperature is lowered to 13.2 degrees Celsius? Well, first, and what you should notice is whenever you have temperature, it must be converted into Kelvin. To do this, I'm going to add 273 to this number. So 24.8 plus 273 will give me a total of 297.8 Kelvin. I'm going to do the same thing with this other number. I'm going to add to it 273, and I'm going to get 286.2 Kelvin. Now I'm going to list my units. Pressure 1, the first pressure, is 1.15 atm. My initial temperature was 297.8 Kelvin. Final temperature, I don't know what this is, but the final temperature was 286.2 Kelvin. So looking at my chart, pressure and temperature is changing. Volume and number of moles is constant, which we always assume unless told otherwise. So this is my formula. P1 over T1 equals P2 over T2. So let's scoot that out of the way so we can do our work. P1 over T1 equals P2 over T2. Now I'm sorry for P2, so let's move the T2 over to both sides, which means multiplying both sides by T2. By doing so, my T2's cancel and I get P2 by itself. So P2 is equal to, now T2 is 286.2, I'm going to plug that in, 286.2 Kelvin. And notice you should always write in your units. This is to ensure that they cancel out and that the units are properly matching each other. So in this case, my kelvins will cancel each other out. So I have 286 times by 1.15 divided by 297.8. You want to try that out in your calculator, and you get a number of 1.11 ATMs. That's rounded. Now you do want to double check and make sure this makes sense. Pressure and temperature are directly proportional. So when one goes up, the other one goes up. Or if one goes down, the other one goes down. So having 1.11, which is less than 1.15, does make sense. Last problem. Now a good best practice would be if you stop the video and took a minute or two to try it out on your own and make sure you know what you're doing. We're going to go ahead and try it for now. The gas has a pressure of 735 millimeters of mercury and a volume of 634 milliliters when the temperature is 298 Kelvin. We're going to go ahead and write these in. Notice we're going to go ahead and write in our units as well. You should never leave your units missing. Now we're going to read on. What is the temperature? So this is the unknown. If the pressure is increased to 1.2 atm and a volume of 525 milliliters. Let's check our units. Temperature is in Kelvin. This is good. Temperature must be in Kelvin. This temperature has unknown units, but it will end up being in Kelvin. Milliliters, milliliters. This is good because volume can be any units as long as it matches. Pressure, 735 millimeters of mercury, 1.2 atm. These do not match. I want to make sure that they do match. So I can use 735 millimeters of mercury. My conversion factor is at 760 millimeters of mercury is equal to 1 atm. When I'm done dividing and rounding, I'm going to get a number of 0.967 atm. This is what I'm going to use up here. I'm going to use instead 0.967 atm. Now notice, for pressure and volume, I really don't care what the units are, as long as the beginning and ending units match each other. Formula-wise, I have pressure, volume, and temperature all changing. So I want to use this combined gas law. P1V1 over T1 equals P2V2 over T2. So let's write that in and plug in our variables. P1V1 over T1 equals P2V2 over T2. Now since I'm solving for temperature, I want to get it by itself on one side. Now this is tricky because this is in the denominator. So I'm going to cross multiply. P1V1 T2 equals P2V2 over T1. Then getting this by itself, I'm going to divide both sides by P1 over V1. Excuse me, divide both sides by P1V1. So now this is my formula. These cancel out, and T2 becomes the second pressure, 1.2 atm. We're going to write in the units, times by volume, 525 ml, times by T1, which is 298 Kelvin. And divide this by P1V1, which is 0.967 atm, and V1, 634 milliliters. So when you're done, T2 is equal to this times this times this, divided by this, or a grand total of 306 Kelvin as my final answer.